In section 2.2, we're going to talk about graphs of a function, which is a visual representation of what the function is doing. And so we're going to begin with the definition. So let f be a function defined by an equation in x and y. So for instance, an example would be y equals f of x, or you can have things that look like 7x minus 3y equals 2, any sort of equation where it has x's and y's. Then the graph of the function is going to be the set of points x comma y in the plane that satisfy the equation. All right, so if f is a function that has x's and y's, when you take a number for x and a number for y, if that makes that equation a true statement when you substitute those values in, then that point x comma y is going to be on the graph. So you kind of have an idea of what graphs look like from high school. Let's flip that question around and ask, when you just have a general curve in the xy plane, how can we tell if it's the graph of a function where x is the independent variable and y is the dependent variable? So that's going to come from recalling the definition of a function. So the defining characteristic of a function was that it's a relation where for each input there is exactly one output. Right, so another way to think about that is we can't have things like this. Cannot have things that look like 3 comma 4 and 3 comma 5 on the graph of a function. Thinking about that a little bit deeper, if there is a point 3, 4 on the graph of a function, then at no other time can the vertical line x equals 3, can it hit the actual curve that's the graph of a function. So more generally, the vertical line x equals a can only hit the curve at most once, right? It might completely miss the curve, but if it does hit the curve, it can only hit it at one spot, which leads us to our vertical line test theorem. So a set of points in the xy plane is the graph of a function if and only if. That's bolded. That statement just means that this statement right here, the first part, is logically the same thing as the second part. So the second part says every vertical line intersects the curve in at most one point. Now this word intersects is essentially the fancy math version of hit. Right, so if you have an intersection of two roads, that's where two roads cross each other, that's where they hit. Let's consider this curve right here and answer these questions listed down here. So for part 1, we want to find what is f of 0, f of 3 pi over 2, and f of 3 pi. F of 0, we go to x equals 0, go up to where that point is on the curve, and it's at 4. So we know f of 0 is equal to 4. Next we have f of 3 pi over 2. We go along the x-axis, find 3 pi over 2, and we see that its y value is 0. And then we have f of 3 pi, go out to 3 pi. On the x-axis, that's now dropped down 4 units. So we have f of 3 pi is equal to negative 4. All right, so 0, 4 is a point, 3 pi over 2, comma 0 is a point, and that's how we're getting these values out. Next, we're asked to find the domain of the function f. Notice that there's nothing to the left, or they're not giving us anything to the left, and there's nothing to the right, which means we're just going to take the x values that have something either above, on, or below them from this graph. Starting at 0, 0 is good because we can plug 0 in and we ended up getting 4. Then as we move along, every single one of these x points either has something above it or something below it until we get to 4 pi, and then there's nothing past 4 pi. So the domain for this picture is 0 to 4 pi. The square brackets means we're including 0 and we're including 4 pi. Next, we want to find the range of the function f. That's going to be, if we were to take this picture and squeeze it all the way down to the y-axis, we're trying to figure out what is getting covered up on the y-axis after we squeeze everything onto it. So starting at 4, there's not going to be anything above 4 because this is going to squeeze down on top there. And there's nothing below -4 that's going to squeeze down. And everywhere in between -4 and 4, there's going to be something that gets squeezed on top of it. So again, it's going to include -4, and it's going to include +4. Next, we want to list the intercepts. So we have x-intercepts and y-intercepts. Let's find the y-intercept first. I'm going to use y-int for shorthand. That's where this curve hits the y-axis. Right? And so it hits at the number 4. When you talk about intercepts, by saying the y-intercept, we already know what the x-coordinate is for the y-intercept. It has to be 0. Likewise, for the x-intercept, we're just going to see where this curve hits the x-axis. And when you say the x-intercept, you already know that the y value has to be 0. So I'm going to maybe write that here just so you can keep track. And so we just need to create a list of all the values where the y is equal to 0. So we have pi over 2, we have 3 pi over 2, 5 pi over 2, and 7 pi over 2. Now let's think about how often does the line y equals 2 intersect the graph. Y equals 2, there's no slope, so it's a horizontal line, and it's just going to start at 2, go right across. So if you were to draw a horizontal line in at the second level, it's going to hit once here, twice, third, 4 times total. All right, and you may want to just draw that in, dot in a horizontal line and see the 4 points of intersection. Next, we want to figure out for what value of x is f of x equal to 4. So if we're looking at our picture, we want to know the x values that have a y value equal to 4. Well, we have one here, another one, and a last one. So x equals 0 works, 2 pi, and 4 pi. And then lastly, we want to find the values of x for which f of x, the y value, is positive. So starting at 0, that is above the x-axis, that's positive. And as we go from 0 to pi over 2, everything is above the x-axis until we get to pi over 2. So we do not want to include pi over 2 because f of pi over 2 is 0, which does not give us a positive value. So we cut that one out. Then from pi over 2 to 3 pi over 2, it's all negative, so we ignore it. Then right after we pass 3 pi over 2, our function goes positive again, stays positive until we get to 5 pi over 2. And so we want to start at 3 pi over 2, go to 5 pi over 2. We don't want to include either of those, again, for the same reason we don't include pi over 2. Then we're negative between 5 pi over 2 to 7 pi over 2, but then from 7 pi over 2 out to 4 pi, we're positive again. We want to include 4 pi because f of 4 pi is equal to 4, which is part of what we answered over here. We don't want to include 7 pi over 2. And so we have 3 intervals. Intervals are sets of numbers. And so we can put these intervals together by taking the union of them. So this is the set of all values x for which the function is positive.